Today we're taking a look at Chapter 4, Goal 14, and this is Example C. We are still working with functions that have a phase shift or a horizontal shift, and we've gotten a little more complex with Example C because we also have a b value or the coefficient of x that has a pi in the radian measure. And we also, that changes our period. We also have a vertical reflection. So we've got lots of things going on here. So before we get started, I just want to review and add one thing to the different types of equations we're looking at. So far, we've learned how to graph y equals a times the sine of bx, or a times the cosine of bx. But anytime we have a horizontal shift, we know that we are adding or subtracting some other constant which causes a horizontal shift. So when you see 2 pi over 3x minus pi over 3, this represents b times x minus the c value. And remember, the reason I have a minus in the formula is because when we take that c value out, it turns into the opposite or goes in the opposite direction. So we've gotten now to a little bit more complex form where we have vertical shifts and stretches, horizontal stretches. I'm sorry, I misspoke here. A gives us the vertical stretch or shrink, B gives us horizontal stretch or shrink, and C gives us a horizontal shift. Would you please take a moment and determine the amplitude and the period length? So your amplitude, remember, is the absolute value of A, and in this case, A is -4, so our amplitude is 4. That means that our max will be 4 units above the x-axis and our min will be 4 units below. And then our period is 2 pi divided by b. In this case, b is 2 pi over 3. So to simplify that, we'll keep it, switch it to multiplication, and flip it. And our period is 3 radians in length. Don't let that bother you because the pi symbol is gone. Remember, pi is nothing more than the exact value of 3.14. Okay, the next thing I want to figure out is my phase shift, and because this is rather complex, I will take the values for bx minus c and place that between the endpoints of the parent function for sine. If you've forgotten, remember our parent function for sine starts at 0 radians and ends at 2 pi radians. So in the last video, we talked about sweeping the fraction or getting rid of the denominator. And I see that my least common denominator here is 3, so I'm going to multiply every term in this inequality by 3. So my new inequality is 0 is less than or equal to 2 pi x minus pi is less than or equal to 6 pi. And that just keeps you from having to add and subtract fractions. Continuing to solve, I will add pi in the middle and on the left and on the right to keep this balanced. And then finally, I'll divide everything by 2 pi. So my leftmost endpoint is 1/2 radian, and my rightmost endpoint is 7/2 radians. And again, this should make sense that pi will cancel since it canceled in our period up here. And let's just double check that our distance from 1/2 radian to 7/2 radians is 3 radians. Because remember, if our period is 3 radians long, then the distance from our start to our finish should be 3 radians. So distance is endpoint 2 minus endpoint 1, and this does check out that our period is 3. Okay, so let's sketch this. I know that my max value is 4, so make sure you have a 4 on the y-axis. And the min is -4, so make sure you have a -4 on the y-axis. Now, remember, our endpoints are +1/2 to 7/2. So I need to shift over to the right from 0 and +1/2, and then I'm going to just count that distance to the right until I get to 7/2. So if this is a half, this distance here, then this would be 2/2, 3/2, 4/2, 5/2, 6/2, and 7/2. And that, again, just helps you to keep your values or your distances as closely as you possibly can. Close to accurate. Still going to be a little bit difficult. Okay, and then we need to divide this into 4 equal parts. So our midpoint, we'll add 1/2 plus 7/2 and then multiply that by a half. So that would be 8/2 times a half would be 8/4, or our midpoint is 2. And again, we could have done that with our dots. 1/2, 2/2, 3/2, 4/2 right here is 2. And then halfway between those. Now, when I get ready to find the midpoint between 1/2 and 2, I can't just count halves to the right because I have different denominators here, 1/2 and 2/1, so just counting across doesn't get me there. So we have to do midpoint. So 1/2 plus 2, I'll change 2 back to 4/2, so I have a common denominator, and then times 1/2. So my midpoint is 5/4. And the midpoint of 2 and 7/2. Again, 2 is 4/2 plus 7/2, and then half of that. That's 11/2 times 1/2, or 11/4. I did it again. I apologize. 11/4. All right, we are graphing sine, and I remember that my A value is negative. And because we have a phase shift from 0 to a half, so a phase shift 1/2 to the right, we will begin at 1/2, down to -4, back to the x-axis, up to +4, and back to the x-axis. So far we have one of the 2 periods for our function. This time, rather than drawing our second period to the right, I would like you to sketch the second period to the left. Remember, we said the period length is 3, so there still has to be 3 radians between the end point and the starting point. So if we sketch this function to the left, 1/2 will be our ending point. So to determine the starting point, we'll take the number 1/2 and we'll just subtract 3. That means we're finding the distance 3 radians to the left. So we will subtract 3. If we were finding the distance 3 radians to the right, then we would add 3. So my common denominator, and that tells me that my starting point is 5/2. So, or I'm sorry, -5/2. So this is 0, -1/2, -2/2, -3/2, -4/2, -5/2. And as you recall, with your second period, you only have to mark the middle and the quarter marks. You do not have to label them. So we'll follow our pattern: x-axis, minimum, x-axis, maximum, and back to the x-axis. And now we have our two periods, both of which are still a horizontal length of 3 radians. We have shifted the function 1/2 radians to the right, and we shrunk our period from 2 pi radians, which is the parent function, down to 3 radians.